Two blocks of unequal mass m, capital M and lowercase m, are hung from the ends of a massless, frictionless pulley, as shown below. The blocks are held in place, and the entire pulley is mounted on a sensitive scale. After the blocks are released from rest, but before either has fallen off the pulley, what is the scale reading? So, according to this figure, we're assuming that the one with mass capital M has more mass than the one with mass lowercase m. And here are some free body diagrams for the two. So here's for the big block, here's for the little block, and then here's the scale with the two ropes on it. So for the first one, you can write this equation. The big mass times the acceleration due to gravity minus the tension must equal the mass times the acceleration. And this is, again, due to Newton's second law. The net force is equal to the mass times the acceleration. And mg is positive because the overall acceleration is down, so it's negative. As for the other case, we have a positive acceleration, so the tension minus the mass times gravity is equal to the mass times the acceleration. This is, make sure you don't make this mistake. You must be using the same units of mass appropriate to the equation. So now we can just simply use tension to find an expression for tension and plug that into the first problem. So from the second equation, we know that the tension is equal to the mass times acceleration plus the mass times the gravity. And now we can just plug this into the second one. Rather, the first equation. And again, this is in parentheses, so the minus gets distributed to both of them. And then now you just move this over to get the accelerations on the same side. You get something like this. Now all you need to do is factor out the gravity and the acceleration. And now you just need to simplify and solve for the acceleration. And then you should get that the acceleration is equal to this right here. It's equal to the gravitational acceleration times the large mass minus the little mass divided by the large mass plus the little mass. So what this is saying is basically that the weight of the large block, or the one that's pulling the whole system down, the acceleration is equal to the force divided by the mass. So up top is the total force. It's the weight of the larger block after the weight of the smaller block has been taken away, because the weight of the smaller block gives some resistance for the larger block, and therefore needs more force to actually accelerate it. The bottom is the total mass of the combined system. So this is simply the total force divided by the total mass. That's what this is saying. So if I erase everything over here, I'm going to write that the acceleration is equal to the gravity times mass big M minus little m divided by big M plus little m. This is going to be important later. But to figure out the scale reading, we actually need to figure out the tension on the rope, because that's what's pulling the scale down and creating that reading. So if you remember from either of the equations, I'm going to use the second one. That tension is equal to, if you solve this, it's equal to the mass times the acceleration plus the weight of the second block. This is done simply by moving mg over. And then we can plug this value in for the acceleration. So we get this really long equation that says the tension is equal to the mass times the gravity times big M minus little m divided by big M plus little m plus the mass times gravity. Now if you notice anything, we can factor out mg again to make this a little easier. this is add parentheses. And then we gotta add this 1 over here. Can't forget about that. And then now, what we're gonna do next is a little weird, but it's something that's necessary to solve this equation. We're just gonna multiply both sides by this. And then this 1, you will also have to multiply this 1. So you get this expression. And then now you can simplify this side. So from that, we get this. M plus m, you have 2 big m's, and these 2 cancel out. So you get that big M plus little m times the tension must equal 2 times big M times little m times the gravity. And then now all we really have to do is just divide by big M plus little m. So your final equation should be that the tension, I'm going to erase all of this, the tension is equal to 2 times big M times little m times the acceleration due to gravity divided by big M plus little m. And then that is the tension force in the rope. But if you look in this diagram, both sides are providing the tension force. So the tension force acting on the scale is actually 2 times the tension force. So this it becomes, you just multiply everything by 2. So the actual force on the scale, or the scale reading, will be equal to 2 times the tension force, or 4 times the mass of the larger one times the mass of the little one times the acceleration due to gravity divided by the mass of the larger block plus the mass of the little block. And this is the final answer to this problem.